Good evening, everyone. Let us get started with our discussion. So, the last day we discussed about the stability of a system before understanding the stability of numerical methods such as forward Euler, backward Euler, trapezoidal, etc. So, we understood the different mathematical definitions of stability. So, to start with Lanup of stability, where it is the definition states that if a system starts very close to the equilibrium point and it remains very close to the equilibrium point for all future time instants, even with small disturbances, it is the system is Lanupav stable. So one example that we took is the nonlinear pendulum without damping, whose equation is given by this. So it's a nonlinear equation, but it's stable because it's a pendulum without any friction, without any damping. So if you give it a small push, it will keep on oscillating near its equilibrium point and never and will not reach equilibrium point. So reaching equilibrium point as time tends to infinity is not one of the criteria of the Lanupav stability, but it is so for asymptotic stability, which states that as time tends to 0, the xt should tends to 0, which is the equilibrium point for this case. One example is probably this kind of a polynomial, which is as you can see that as t tends to infinity, the xt tends to 0 because yeah, this is 1 by under or x0 divided by under root of t. uh, but it does not tell this does not specifically tell about how fast the system needs to go to the equilibrium point. The third definition tells about that. So it tells that the the system should reach the equilibrium point at least as fast as an exponential delay, which is this. So the system has to be as fast as that, as at least as fast as an exponential. So you can say, so the second case which I have taken, it is asymptotically stable but not exponentially stable, but anything that is exponentially stable is definitely asymptotically stable also. And we also discussed that for linear systems, asymptotic stability and exponential stability are the same. If it is asymptotically stable, it will be exponentially stable also. Then we looked at the stability of numerical methods of a system, of a simple system dx dt equal to lambda x. So for forward Euler representation is the first one, backward Euler representation is this, and trapezoidal is this one. So it tells us, so from the understanding of about stability of a system, it should decay to the steady state or the equilibrium point, which is 0 in this case. So in this case you can see that all these numerical method, the equation for that can be written in this format, where xn plus 1 is equal to some multiplying factor into xn, which is the previous instant value of x, where z is nothing but multiplication of lambda, which is the coefficient here, and h is the step size. So the numerical method to be stable, this factor rz, the magnitude of this has to be lower than 1. So for forward we also we made all these factors, we as we solved for equality, that when these factors are magnitudes are less than 1, and we derived that for forward Euler actually h has to be lower than 2 by lambda, which is nothing but 2 times the minimum time, basically the time constant of the system. But for backward Euler and trapezoidal, it is any value of step size which is greater than 0, the systems are stable. Forward Euler, if the step size is larger than this, then the system will not be stable. Also we looked at the example of a stiff system, where where very different time constants are there, like for an example motor drive where the electrical time constant is in milliseconds, but mechanical time constants could be in seconds. So for those systems, if we want to solve using forward Euler, then we have to use some step size which is quite small compared to the minimum time constant, which is the electrical time constant. But you understand that for mechanical, for solving it for longer time, it will take a lot of computation and time. But if we want to but and using forward Euler, although it is simple, it is not possible to solve quickly, because we have to, for stability we have to use a very small time step. But backward Euler or trapezoidal methods, implicit methods, can be used even with a relatively larger time step, and stability will not be affected for systems such as basically stiff systems such as motor drives, or similar systems where any system where time constants are quite far away from each other. Now I will remove this presentation and go to the MATLAB simulation where uh, I will show the impact of step size and methods as discussed theoretically here. So I will share this screen. Is my screen visible?
Yes, sir.
Okay. So this is for the system parameters. So armature time constant was 20 millisecond. Then for field it was 25 millisecond. Mechanical was 2 seconds, right? And we were solving it for 30 seconds, and the step size we had given is 1 millisecond. So I'll run so that all these all these values basically come to my workspace. And let me go to the DC machine model. So in this case, if I go to the model setting, model setting tells us that it is fixed step, and time step is t step, whatever 1 millisecond I have defined, and the solver is basically OD1 Euler, which is forward Euler method. So I'll keep this as it is and solve the system. So in this case the step size is 1 millisecond, and the minimum time constant is 20 millisecond, which is the armature time constant. So it should be stable. And if I look at the VF and IF, if I zoom in horizontally, then you can see that this is the type of response that you expect in the field winding. It is a first order response. And let us see what we were doing in the simulation. We were basically first exciting the field winding, then giving increasing the armature voltage as a ramp. Then after that we were reducing the armature voltage in steps, and we were also looking at the response of how armature current changes, and the back EMF is another thing that is indicative of speed here. So if I zoom in any one of these cases, then you can see that after steady state is reached, and if you give a step change in the armature voltage, then there are some oscillations in the armature current, and back EMF also there are some oscillations, and after that it becomes steady in the next to the next steady state point. So this is the correct response, because we are solving with it with very low step size. Now let us see what happens if we keep it forward Euler only, but increase the step size beyond something. So let us increase it to say 5 milliseconds first. Now if I go to the field case, you will be able to say that it is reasonably good in this case also. And if I go to the armature one, you see some kind of different response. So it seems that oscillations have increased, whereas there was little oscillation, or not this much oscillation in this case. So you see that there is some impact of, or the this solution is not correct, because we expect that whatever solution we got for the minimum time step, or so how to understand it is the correct time step. If you further refine it, the solution should not change further. So you can see that in this case there are a lot more oscillations as you are as you have increased the step size. Now let us again go back to the step size thing. We made 5 millisecond from 1 millisecond. So to understand whether the 1 millisecond response was accurate enough, let me reduce this to 0.1 millisecond and run it. Right, in this case field 1, there is no problem, it is first order response. Now if I go to the armature one, you can see that this is similar to whatever we obtained. There are only say one or two cycles of oscillation, and after that it reached steady state. So even if we refine it further, the solution will not change. So it tells you that the refinement of the step size is actually enough. So further refining it will not improve our accuracy. But as we have already seen, if I make it 5 milliseconds for the forward Euler and run it, then you could see that the solution has actually changed drastically, and the step size is not actually enough to give reliable results. Now if I increase the step size further, so let me make it 10, which is half the or fastest time constant, which is armature time constant for this case. In this case, if I run, then MATLAB or SIMULINK flags an error, because it understands that forward Euler with this type of time constant, this type of system parameters, it is not enough to produce some reasonable results. So because MATLAB Simulink has been already given, so those conditions and other things, so MATLAB Simulink does not solve, and it flags that there is some error or there is some mistake with the inputs. So now let me change the solver type. Now let me change the solver type to say backward Euler. So in this case I am not changing the time step, I am only changing the um, method to ODE1BE, which is first order backward Euler integration method. So if I run it, the time step still remains the same, which is 10 millisecond, because we already know what the correct solution should look like. So if I solve it, you can see that field winding, it remains. So first thing, it solves. So MATLAB Simulink does not flag any error, so it is able to solve. Now the next thing is field thing is accurate only, and the armature one, if we go, then you can see that still there is some compromise about, because you are solving it once every 10 milliseconds, so you cannot expect a smooth response, but at least there is not oscillation, there is not an increase in oscillation as we saw for the case of forward Euler when step size was increased. So more oscillations is an indication that system is going unstable. But in this case, although accuracy is compromised because you cannot expect everything, uh, if you are solving at every 10 millisecond, then you cannot expect a smooth waveform, right, if the dynamics are much faster. But at least it is solving and it does not lead to instability. And another thing is, if this is a stiff system, so there are many widely different time constants at play there, but you are able to solve for the steady state point reasonably quicker compared to forward Euler with a very fine time step, right. This clearly tells you uh, the usefulness of implicit methods such as backward Euler. I am not so I will only stick to backward Euler. Now let me close it, and just to show the efficacy, or that it does not go to instability for even larger time steps. So the minimum time constant was 20 milliseconds. Now let me make it 30 milliseconds. So 30 milliseconds is even higher compared to the armature winding time constant as well as field winding time constant. So let us see what happens. So in this case, if I run field winding, you can see the discretization. So solution is happening only at this instance, and that is why there is the smoothness is not there in the waveform, but that is expected because you are solving for only those points, but it is reasonably accurate. And this is the armature winding voltage, current and back EMF. Here also you can see that, yeah, this is the discrete nature of the points can be seen, but it predicts the output, steady state output, quite accurately. It is not capable to model the transient the smoothness of the transient response, but it does not go to instability. It does not become unstable, even if I am using a uh, very coarse time step. Now let me go back and use say 1 millisecond of time step for the backward Euler method only. Then actually, if you compare the simulation time, here it may not be obvious because it's quite quick, and in some instant it is being solved. But if you actually use clock and see the simulation time, then you will find that solving forward Euler with 1 millisecond time step is expected to take lower time or lesser time compared to backward Euler, because backward Euler is an implicit method where it needs to do certain more calculations in order to solve, but it is more stable for stiff systems. So here in an instant it solves, and you can see the results. It's a field winding first order response, and the armature one also you can see that, yeah, this is the response that you expect, right. So I'll is there any question on this?
No, sir.
Okay, then I'll stop sharing this one, and again go back to the presentation and continue with the new discussion that I am going to start today. So I hope my screen is visible. Yes. Is my screen visible?
No, sir.
Oh. It came now, right?
Yes, sir, it's visible.
Okay.
Yes, visible, sir.
So now let us, so still now what we have been discussing the different mathematical models of system. So you have discussed about differential equation model, which is a continuous time model. Then we went to state space model, which is same thing as a differential equation model only, but written in a different way in terms of states of the system. And after that we went to difference equation model, which is the discretization, that is discrete time model of a system. And for discretization we needed some numerical method, that is why we discussed the forward Euler, backward Euler, trapezoidal. And also we needed to understand about the step size and stability of numerical methods, that is why we have discussed all this stability stuff and other things. Now all these methods like differential equation, state space, and difference equation, they are valid for both linear, linear time variant, linear time invariant, non-linear systems. So those are valid for all cases. But the fourth one, that is transfer function model, which we are going to start, is only valid for linear time invariant systems. So let us, before going to that, let us, and that is frequency domain. So all these things are time domain. First two are continuous time, and the third one is discrete time. The transfer function model, the transfer function model is the first frequency domain model. So frequency domain model, we'll have to understand that, understand the motivation for moving from time domain to frequency domain, and what advantages do we get by doing that. And it is valid only for linear time invariant systems. So we have to understand linearity, and um, first, what is the motivation to move from time domain to frequency domain. So let us try to understand linear systems. So to a lay person, linear means linearity means some straight line. So the, if say input of a system is u and the output of a system is y, and if input and output are related by say k into u is equal to y, that is they are related by a linear operator, or they are just a scaled version of each other, the output is a scaled version of the input, then the relationship between output and input will be a straight line, right. So this is with slope k, and if you give any input say u1, you will know what is the output y1. If you give some other input u2, you know what is the output y2. So this is the definition of a linear system to a lay person. But it is not complete, but we can understand the important properties or the most generic properties of a linear system by using this example. So the first thing is, so any linear system has to obey two properties. One is scaling property. You already know about this, right? What is this? So if input is scaled by some constant real number say alpha, then the output will also be scaled by alpha. So what is the meaning of this? So if you have this one ku into y, so if you make the input, so if so let us say, so it has to true that if instead of you give alpha u as the input, your output should be alpha y. So let us see. So if you multiply both sides by alpha, so alpha into k into u is equal to alpha into y. So if you separate k, because all these are real numbers only, and you can take alpha u together and alpha y together. So that means if alpha u is the input, alpha y is the output. Now the second property is the superposition or superposition theorem. So superposition has to hold. So what is the meaning of superposition? Say you have some input u1, the output is y1. If you have some other input u2, you have some other output y2. If you sum the inputs, the output should also be some version of the two separate outputs. So this also can be proved. So our system equation is ku equal to y. So for u1 input, this is the equation. For u2 input, this is the equation. So you can simply sum these two equations. So you will have k u1 plus k u2 is equal to y1 plus y2. If you take k as common, because it's a real constant quantity, so u1 plus u2 equal to y1 plus y2. So it is of the same form as the original equation. So still this is the theorem. So superposition holds for this type of a system. Now you can see that this is a very simple example of a system, but actually this actually uh, holds for a larger number of linear operators. So multiplication by a real constant quantity, that is one multiplication operator, and there are such operators. So if any operator, uh, say any operator, say L can be multiplication, it can be addition, it could be differentiation, it could be integration, or any operation, basically any mathematical operation or operator that satisfies the two properties of linear systems, then that operator L will be called as a linear operator. So for a linear operator, the properties are like, if linear operator of alpha y has to be alpha into Ly, where alpha is a real constant quantity, and the second one is linear operator of y1 plus y2, that has to be linear operation on y1 plus linear operation on y2. So any operator that satisfies these two equations will be called as a linear operator. And then what is the most general or more general definition of a linear system? So say L1 and L2 are two linear operators. U is the input, Y is the output, right? Then if the system equation is written or can be written in this form, that linear operation on y is equal to linear operation on u. If the system equation can be written in this form, then the system has to be told a linear system. Now let us see some examples of first linear operators. We are talking about dynamic systems, so differentiation ddt is a linear operator. Similarly, any higher order differentiation, that is also linear operator. Integration of a thing with respect to time, that is also a linear operation. So all these things are linear operation. And linear combination of linear operators is also a linear operator. What do I mean by this? If say I have second order differentiation as a linear operator. Linear operation means addition or subtraction. So if I add it with ddt, and this becomes my new operator, because this thing is a linear operator, this thing is also a linear operator, then this whole thing is also a linear operator. Similarly, if I add a multiplication, say multiplication by constant k, and this whole thing, because this multiplication is also a linear operator, so uh, this is also a linear operator. So that means any linear combination of linear operators is also a linear operator. So in general, any linear system, so let us say linear system whose output is say x. So right, so separately second derivative, first derivative and k, this is a linear operator, and first derivative plus say k2 or 1, 1 is a special case of k2 equal to 1, this is also linear operator. So this differential equation, this is a dynamic equation, and uh, uh, on a straightforward basis it may not appear to be a linear system. So in the to the most uh, lay understanding, that input and output are linearly related, but like it's a straight line relationship, it may not be like that, but because it's a linear operations are done on the input as well as output in the equation, in the system differential equation, so it's a linear system. So in general, say is the screen gone? Okay, I think the screen had just disappeared somehow. More general example can be like where there on one side you have say a equation. So this is a linear operation uh, on the input or on the output, and say a mth order differential equation that describes the operation on on the uh, on the input. So this is also an example of a linear system. So a system whose whose differential equation is can be written in this format with linear operators. More generally, L1 of output is equal to L2 of input, or yeah, there could be more terms, there could be different linear operators. Only thing, no non-linear operator should be there, and then it is a linear system. Now it's obvious, it's very natural to ask that why linear systems are so important, or why do we need to learn uh, about linear systems. So first thing is, it has to be useful. So whatever we are learning has to be useful, and has to or should be applicable to most of the systems that we come across in nature. So linear systems are actually are very commonly found in nature, or the systems which are found in nature with certain assumptions and approximations can be expressed as a expressed as a linear system, and the linear system theory can be applied to get reliable results. So this is the first reason. First reason is it is very commonly found. And because it is very commonly found in different systems found in nature, so it's useful. So let us see some examples. So let us say, whatever class 11 or engineering mechanics, you must have come across a mass spring damper system, right? Some spring and damper is connected to a mass m1, and say some other spring, some other damper is connected to another mass, say m2, and you are interested to find out the displacement of u1 u2. Then this mass spring damper system, this is this so these equations can be written. This system is basically a linear system. And also electrically, because we are electrical engineers, so you know that all electrical components, all everything can be represented by only three components, three electrical elements, which are resistance, inductance, and capacitance. So this is some voltage input. You have R, L, C. So R, L, C circuits, they are also linear. So the differential equations for uh, the mass spring damper system or the RLC circuit can be written as where can be written as in this format only, the same format that I have discussed. It's a linear uh, s plus an into x equal to u. So in this format, or there could be some linear operation on u also. So it could be, so all these systems, so like I have given two examples. One is mass spring damper system, another is the RLC circuit. So the differential equation are of this form, which are, so all these coefficients of the differential operators, they are constant quantities. So such systems are linear time invariant systems. So most of the things in electrical engineering, including motors and other things, although there are non-linearities, they can be accurately or reasonably, with reasonable accuracy, can be expressed with RLC circuits only. You are also, you know, the steady state equivalent circuit of induction motors or synchronous motors, or even the transient circuit of motors. Even if motor is such a complicated thing with so many things, magnetics and other things, if it is, there is the magnetic nonlinearity, or the magnetic nonlinearity is or neglected, then the motor can be represented with linear circuit only. So actually it's useful. So these two examples that I have given are examples of linear time invariant system. Now next, let us have some other type of example. So say we could also have some oscillator where the equation could be so the exact equation, if it is so the equation is, if it is written, then you will find that it is of this form, right? So here you can see that the coefficient basically varies with time, so it is a linear, it's still a linear differential equation only, but the coefficient is a function of time, so it's a linear time variant system. So these are two examples. The third one I'll take is, say we have two bodies, so body of mass, body A, body B, which have certain temperatures, so Ta, Tb, where Ta is greater than Tb. What happens if these two bodies come in contact? Then there will be heat flow from one body to second body. So if we assume heat flow only along the x-axis, then the heat flow equation form is something like this, where T is the temperature, uh, so this is the form of the heat flow equation. Uh, um, uh, I'm not going to explain this, but this is the form of the first or the one axis, or 1D heat flow problem, where heat flow happens only in the x axis. So you can see that it is not uh, a lumped, or it is not ordinary differential equation, but it is a partial differential equation. So still it is a linear system only, but only thing, it is a distributed thing, so it's a linear time invariant distributed system, because we are using partial derivatives instead of ordinary derivatives. So all these are similar, like heat flow equation or wave equation, all those equations are like distribution, linear time invariant distributed systems, where instead of ordinary differential equation you have partial differential equation. Now why linear systems are important, point number 2. So for a given input, an initial condition, response of the linear systems can be explicitly derived. So if suppose you have some system, and in the system you have different state variables. So for your solution to successfully carried out, you need the, say you have different states of the system. So for the solution, you need to know what is the initial condition, what are the initial conditions of the state variables, and what is the input. So if you know these things, then you can actually explicitly derive the nature of the response. But for nonlinear systems, it is not the case. For just I'll take one example. Say I'll take a linear system of this form. Say x double dot plus x dot plus x equal to u, where x is the x is the output. So you have two state variables here. So if you have just a common thing, if you have a higher order differential equation, if you want to find out the states, then easier way is, so you take the first state as the state variable, say x, and then you take the next state as the differentiation of the state variable, right? And then the third higher order, like the highest order thing, x double dot, will now become u minus x dot is nothing but x2, and x is nothing but x1. So it is in the form of state space. So if you have a second order differential equation, then you will have two states, where the first state is the variable itself and the second state can be taken as the first order time derivative of the variable, right. So for this case, suppose you have a third order differential equation, so then you need to know the three initial conditions of the three states. Now, yeah, we took this example of, this is a linear system, as you can clearly see. Now let us take a nonlinear system of this is quite similar. So yeah, say this is 1 minus x square. So this is a nonlinear equation because you have x cube happening here. So it's a nonlinear equation, and you can afford a linear, so x square or x cube or x to the power something other than 1 is not a linear operator, so it's a nonlinear system. So let us see the input is 0 for both these cases. Now let us see, x dot initial condition is 0 and x initial condition is say something x 0. Now similar initial condition is there for this nonlinear case also, and x 0 equal to x 0, right. Now if you actually solve this system for different values of x 0, now I will just give you some sample response what you will get. Say this is xt and this is time. Now say this is 0, this is 0.5, 1, you have 1.5, you have 2. So if you take x 0 equal to say 0.5, then say system response may be something like this. There is some small undershoot and after that it settles down. Now if you take initial condition as 1, then also for linear systems you will have the nature of response exactly same, and after a few oscillations it will settle down. Even if you take now, if say you take 2 as the initial condition, x 0 equal to 2, you will still find the nature of response to be the same compared to the other responses. So that means if so the nature of the response for linear system does not change with the amplitude or the value of the initial condition. The nature remains the same. If you know it for one initial condition, you know it for all initial conditions. But for this case of a linear system, I will just show the typical or the response that you are expected to get if you solve it. So this is time axis, this is xt, the same thing say 0.5, you can take 1, you can take 1.5, all these things. Now if you actually solve this for initial condition of 0.5, then you will see that it is a response quite similar to the linear system response, undershoot and then it settles down. But say if you solve for some initial condition of say x 0 is equal to 0.999, then you will find that response is quite different. It is something like this. So you can see that here it exponentially falls to false, and then after a few oscillations it settles down. But here the falling nature is not exponential. It is initially it is something like a parabolic fall, and after that it settles down. Now this is for initial condition of 0.999. Now same system, if you actually solve for initial condition only slightly different, say x0 is equal to 1.001, then you will find that actually the system response goes like this, it blows up like this. So for nonlinear systems you could have different type of response for different initial condition magnitudes, but for linear systems, the why it is so beautiful is, if you know the response for one initial condition, the same nature will be followed for all initial conditions. So if you know the nature of the response is independent of the magnitude of the initial conditions. Now let us go to the third point. Because the scaling property and the superposition is valid for linear system, so if you know the response of a particular type of input, say you know the response due to one particular input, by studying the output response, it is possible for you to come up with the response of another output, another type of output, sorry, another type of input. It is possible for you to come up with the response for another type of input for linear systems, but that is not possible. For an example, suppose you know that if you give input a step, you will find the output, say y, as some this type of a response. If you know this, if you analyze this properly, it will be possible for you to predict without doing any further analysis, that if you give, instead of a step change, a step input, if you say give a sinusoidal input, how the response will be, it will be possible for you to come up with that without doing any analysis. So it is also another utility of linear systems, or another beautiful proper thing about linear system, that if you know the response due to one type of input, it is possible for you to derive the response for another set of output, another set of input. So this is another point. Now if you want to solve, so for solving linear systems means what, you are given a linear time invariant ordinary differential equation. So say you are given one equation like this. This is just a sample uh, form of linear differential equation, ordinary differential equation that I have taken, say plus a n x is equal to u. So let us say this is a sample linear time invariant differential equation that I have. So for a given input, you have to solve for the x, which is one of the state variables, and it is also say the output. So for that, what do we need to do? You have to solve for x. So for solving linear time invariant ordinary differential equations is well established, and there is a specific procedure you need to follow. First, you need to find the complementary function, say, and what is the meaning of that? It basically gives the transient response or the transient output. So say it is x transient as a function of time. So the complementary function, the whatever you will get as the solution is the x transient. And how to solve this? This is solved by putting the u this is solved by putting u equal to 0, and the equation basically turns into a homogeneous differential equation. So n minus 1 d t n minus 1 plus 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 a n whole thing x is equal to 0. This is a homogeneous differential equation, and if you express this, as a uh, some nth order equation, algebraic equation, and if you solve for the roots and say you get the n roots of the system or of the equation, then if you already know that if all are distinct, then the transient response x transient as a function of time, which is the complementary function, it will be of the form e to the power lambda 1 t plus a2 e to the power lambda 2 t plus dot 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 a n e to the power lambda n t. So this is the transient response of the system. Now what about the other part, which is called as the particular integral? If you follow the engineering mathematics textbooks which are taught in the first or second years of the Bachelor of Technology courses, now you will find a step by step method to find out particular integral. So particular integral, it gives you the steady state solution. So say x steady state as a function of time. So once you know the transient complementary function, which is x transient of this form, and if you solve the particular integral and it comes to be something, say x ss as a function of time, then your entire solution xt is nothing but the summation of the complementary function, that is xtr as a function of time plus x ss as a function of time. So this is your complete response, and you need to you need to know the initial conditions. So because it's a nth order differential equation, you need to know uh, um, the states. You will have n states of the system, and you need to know the initial condition for all those n states, and then it will be possible for you to find out these coefficients a1 to an, because you have n unknowns, you have n possible equations, so you can find out that. Now there are specific methods to solve for particular integral, but I will stop with uh, solution of particular integrals for common electrical inputs. So what are those? Say so one very common thing is DC. We can have DC input, and in that case our input, say let us take an example to start with. So let us take the example of some voltage source or some general voltage source. AC or DC will discuss later, will start later. So this is a switch, and we have some inductance and we have some resistance. So this is a basic RL circuit with some switch and some voltage source. So at t equal to t equal to 0, if we turn on the switch, how the current will be, that is what we are interested to solve. So at t equal to 0, as it is suddenly turned on, then the differential equation of the KVL equation will be nothing but V equal to L di dt plus Ri. Now you can see that this is a linear differential equation with constant coefficients, right? So first let us try to so irrespective of whether it is what is the input here? It is V. So V is the input, and the state variable is I. this is the state variable in this case as well as output. So I is the state variable as well as output. It's a first order system, so only one state variable is there. So irrespective of whether our V is DC or AC or something else, the solution of the complementary function remains the same. So how to solve the complementary function, or how to get the uh, transient solution? We need to make V equal to 0. So we get LDI dt plus Ri is equal to 0. If we write this equation, say L d plus R is equal to 0. So d is equal to nothing minus R by L. So this is our solution for t. So our complementary function will be, our I transient as a function of time will be some constant a into e to the power minus t by R by L. Right, so it will be a into e to the power minus okay, it is the form is a e to the power lambda t. So it will be a e to the power minus R by L into t. Right, this is the transient solution. Now let us try to solve for particular integral. Now for first case, our assumption is V is equal to VDC. So if V is equal to VDC, what is the steady state solution? For getting steady state is straightforward. We need not solve all things of the particular integral. We just need to put di dt is equal to 0 to solve for the steady state equation, and it will be nothing but I steady state is equal to, or basically R into I steady state is equal to VDC. So I steady state is equal to VDC by R. So the solution in this case IT will be VDC by R, which is the steady state solution, plus A into e to the power minus R by L into T. Now we know the initial condition at t equal to t0 there is no current flowing through it. So if we put t is equal to 0, then I of 0 is equal to 0. If we just put this, we will get A is equal to minus VDC by R, and our solution will be IT is equal to minus VDC, or VDC by R minus VDC by R into e to the power minus R by L into T. So you will get VDC by R into 1 minus e to the power minus R by L into T. So you see there is no need to go for Laplace solution for such a simple first order differential equation, and you can simply do it by intuition. First thing is getting the lambda 1, or if it is RLC you need to get lambda 1 lambda 2, and you can get the complementary function, and steady state is easy. So you can get the response within a few minutes. Now say if it is AC, how to solve? So I will just remove this portion. If it is AC instead of DC, so in that case our input is some Vm sin omega t, right? If you have, now I will put Vm sin omega t is equal to L di dt plus Ri. If you follow the steps of the particular integral, it could be it would take some tens of minutes to, at least some 10 minutes to come up with the solution. But why to solve for all those things? You already know for these RLC circuits, you know what is the steady state solution. That comes from your phasor analysis. So you know that if your voltage is a sinusoidal quantity, your current for RL circuit will be lagging behind that by some angle phi, and the amplitude also will know, you know. So the I steady state in this case is nothing but Vm by Z, which is the impedance, into sine of omega t minus phi, where Z is under root of r square plus omega L square, and phi is nothing but tan inverse omega L by r. So you already know from AC analysis, from phasor analysis, you know the solution. So there is no need for you to go through all the either the Laplace transform and solve for by doing inverse Laplace and all those stuff, or you need not do the particular integral solution by the mathematical method that is taught to you in the first year. For electrical circuits, simple first order, second order circuits, it's just you can solve it within a few minutes, and you can immediately get the steady state solution. Now if you want to write the complete solution, it will be the sum of these two only. So IT in this case will be I transient, which is a into e to the power minus r by L into t, plus Vm by Z into sine of omega t minus phi. So this is your solution. And if you again put at t equal to 0, I of 0 equal to 0, and you will be able to get the value of a. This can be solved graphically also. Erase this portion and show the graphical meaning of what is happening. So in this case, the voltage is sinusoid, and it starts getting applied at t equal to 0. So this is time, this is voltage of time, right? Voltage is 0 at t equal to 0. Now you know the steady state solution of current. It will be lagging behind. It will be lagging behind the voltage by some angle. You know the, and this is nothing but the time corresponding. So omega into, or basically phi divided by omega. This time is nothing but that. So this is the steady state solution. Now if we want to but in this case our current cannot rise from uh, this initial value, like say I1 is this value, which is the if t equal to 0 is put in this equation, then whatever negative current you will get, that is that is nothing but Vm by Z into sine phi, that is minus of Vm by Z into sine phi. This is the value of I1, right? This is the value of I1. But because you are turning on the switch at t equal to 0, then your current has to rise from 0 only. So that means your total solution I has to rise from I equal to 0 at t equal to 0, has to rise from there. So that means the value of the transient, or the magnitude of the transient solution at t equal to 0 has to be I1. So it has to start from I1, positive I1. And because we already know the nature of the complementary function, which is nothing but a into e to the power minus t by tau, right? Uh, where tau is equal to L by R. So you know, because at t equal to 0, this thing I transient is nothing but A. So you straight away know that your I transient, or basically your A, is nothing but I1. And I1 basically falls as an exponential function. So your transient uh, portion of the solution looks like this. Now how will the complete solution of, so this orange one is nothing but I transient of t. Your complete solution, which is I equal to I transient plus I steady state, will be the summation of I transient and I steady state time by time instant by time instant. So initially it will start from this point. So at this instant, this is the blue one is the current and the orange one is the transient, so it will be here. So you can see that the first peak will be little bit higher, and after that probably based on the time constant value that you have, it will settle down. The transient part will go very close to 0. So your solution will be something like this. So initially there will be some transient, and after that it will go into steady state. So this is your complete solution. So you can see that by looking at this graph or the waveforms, you need not even solve any algebraic equation. You can just straight away solve for uh, the first order, second order ordinary differential equations very quickly, uh, by inspection only, within minutes. Only within 1 minute probably you will be able to solve this. So it's very important for engineers to understand these quick uh, to know these quick ways of coming up with solutions without depending on either complicated or involved methods such as um, Laplace transform, inverse Laplace transform and other things, or to rely on software. So for these simple things you can do this quickly. So you have understood how to solve a linear order time invariant differential equation and do it for common inputs, common electrical inputs. But for generality, we have to do it for any arbitrary input. So on the next day we will see how to actually do it for any arbitrary input. Say if you have your input as any arbitrary, it is not DC, it is not AC, it could be triangular, it could be trapezoidal, it could be quasi square wave, whatever, all it could be some arbitrary waveform also. What is necessary to get so some basic thing which if you know, you will be able to readily come up with the solution for uh, this particular complete solution quite easily. So that will why we need to go to frequency domain, because of the complexity of that. So yeah, we'll stop now. Any question from whatever I discussed today?
No, sir.
Okay, so we'll stop. Good night.